All right, good morning, everyone. My name is Mackenzie Woodman. I'm the Geology and Remote Sensing Application Specialist here at Spectral Evolution. And today I'm going to be going over low and high sulfidation deposits from a spectral perspective. So we're going to go over the background, talk about low and high sulfidation deposits, and then talk about some of the mineral spectra that they can use to vector them and why it's important to the industry. So first, I'll introduce Spectral Evolution. Spectral Evolution is the leading manufacturer of high-quality UV vis NIR spectrometers and spectroradiometers. Today, we'll be talking about our spectrometers. We were established in 2004, and we're located in the Boston area in Haverhill, Massachusetts. So we're manufactured in Massachusetts as well. So our primary applications are in anything hyperspectral applications. All of our instruments are hyperspectral. Remote sensing and vegetation, mining and geology, which is what we'll be focusing on today, as well as photonics and calibration transfer. So this is our lineup of our field portable spectrometers. All of our instruments are field ruggedized to be taken into the field in order to scan rocks and samples in the field, bringing lab quality data out into your field days. So we have all of these instruments are separated by their spectral resolution. So here we have the OR Express, which would be standard spectral resolution at 2.88 and 6 nanometer resolution. Our OR Explorer, which is considered high spectral resolution at 2.7, 5.5, and 5.8. Full width, half max spectral resolution, and our OR Expert, which is ultra high spectral resolution with 1.5, 3, and 3.8 nanometer resolution. So this is a picture of it being used in the field. The most common way to use this instrument in the field is our contact probes. This allows you to supply your own light to analyze the mineral spectra, so it allows for adequate energy across the entire UV vis NIR spectrum. So having a high energy light source within in a controlled environment allows you to get better mineral spectra. So we have two different options, a 10 millimeter spot size as well as a 3 millimeter spot size to get more targeted on mineral grains. We also have a field ruggedized tablet. The tablet runs on a Windows operating system with an integrated GPS. So your GPS coordinates will be integrated into your metadata with every scan. Easy ID, Darwin's Easy ID, which is our spectral matching software, is integrated within the tablet as well. When you're running Darwin, it can run Easy ID as you're going, matching to mineral library spectra. And all these library spectras are fully customizable, so you can pull in custom libraries or existing libraries that you've purchased with the instrument. And all of your data can be exported as an ASCII file. Our files are called SED files, but they're ASCII format. And so they can be processed very easily in third-party softwares. So speaking of those built-in mineral libraries, it will come with the USGS SpecLib library, which has 470 spectra and 314 minerals. For purchase is the SpecMin library, which has 1,528 spectra for 494 minerals, and the GeoSpec High Resolution library, which is 688 spectra for 239 minerals, which is collected with the highest resolution spectrometers on the market. So, like I said, you have the ability to create your own mineral libraries. The mineral scalars are integrated into the EasyID software, so you can get all of that data in batch processing afterwards, which I'll speak a little bit more about batch processing later in the presentation. But all of our softwares can be run on a PC or a tablet. So if you'd like to just collect your scans in the field and then batch process all of them afterwards, that's also an option. So to talk about low and high sulfidation systems from a spectral perspective, first I'll overview epithermal gold deposits, then talk about low sulfidation, and then high sulfidation deposits. So to start, epithermal gold deposit types. Types of epithermal precious metal deposits are differentiated by the acidity and chemical composition of the fluids that form them. So you'll have two end-member styles of epithermal gold deposits. You have the low sulfidation deposits and the high sulfidation deposits. Low sulfidation epithermal systems form from a neutral to mildly acidic fluids that come from deeper crustal levels, but are typically less connected to magma sources. And high sulfidation forms from acidic, sulfur-rich fluids from deeper magmatic sources. These react with surrounding rocks, altering them chemically, and deposit there. So epithermal gold, the gold forms in hydrothermal systems in both low and high sulfidation areas. They form in the uppermost part of the crust at less than 1,500 meters below the water table and at temperatures below 300 Celsius. These are often found in Cenozoic age, volcanic arcs, hot springs environments, and calcium alkaline magmas. So epithermal gold, quartz veins, stockworks, and breccias carry gold, silver, and variable amounts of important minerals. They form epizonal to near surface environments, and these ores commonly exhibit open space filling textures associated with volcanic related hydrothermal to geothermal systems. So hydrothermal minerals in epithermal gold. Many hydrothermal minerals are stable over limited temperature and or pH ranges. Mapping distributions of alteration minerals in areas of epithermal prospects allows zonation to be reconstructed and vectoring. Alteration minerals are critical to distinguishing the style of deposit, so identifying if it's low or high sulfidation. Low sulfidation geothermal environment, boiling of liquid leads to precipitation of gold, silver, and other minerals and veins. Silica sinters can be the surface expression of these veins, accompanied by nearby zones of superficial steam heated acid alteration. Silica sinters are a form of opaline silica that is found around hot springs and geysers. So here's a diagram of low sulfidation epithermal vein systems. These deposits form in both subaerial, predominantly felsic volcanic fields and extensional and strike slip structural regimes and ilic arc or continental andesite stratovolcanoes above active subduction zones near surface hydrothermal systems ranging from hot springs at surface to deeper structurally and permeably focused flow zones. The ore fluids are relatively dilute and cool solutions that are mixtures of magmatic and meteoric fluid mineral deposition as the liquid undergoes boiling and decompression. This is a model of a low sulfidation epithermal system here for your reference. Here you can see the advanced argillic zones under the acid springs and the tuff ring and proximal sinter, as well as the argillic alteration shown by the smectites and illite alteration caused by upflow and outflow. So you can see at the top there, the tuff ring, proximal sinters right in the middle. And you can see the upflow and outflow shown by those black arrows. And the white arrow for meteoric recharge. So moving on, the alteration types of low sulfidation systems. Silicification is extensive within ore zones characterized by multiple generations of quartz and chalcedony. This is commonly accompanied by andaluria and calcite. Pervasive silicification occurs within vein envelopes. Then we have sericite, illite, kaolinite assemblages, flank zones of silicification, and represent argillic alteration halos. Intermediate argillic alteration consists primarily of kaolinite, illite, and montmorillonite, typically forming adjacent to mineralized veins. Advanced argillic alteration is defined by a kaolinite alunite assemblage and may develop near the tops of mineralized systems. And propylitic alteration dominates at depth and along the peripheral zones of the system. Buddingtonite may also be present locally. So, to talk about some of the spectra, we have the quartz, sericite, and delaria minerals here. The assemblage is characterized by quartz, andalaria, and sericite. The left plot shows that. Displays a dominant mineral assemblages. So on the left plot, we show quartz, illite, muscovite, and pyrite here for your reference. On the right here, we show broader mineralogical associations, including illite, mixed layer illite, smectite, montmorillonite, quartz, andalaria, calcite, dolomite, kaolinite, and pyrite. Andalaria varies from alteration around veins and fractures in permeable zones to selective replacement of that plagioclase in the alteration envelopes, making it important for alteration zones. Now, another type of silicification is shown here in this plot. Silicic alteration is pervasive replacement of the rock by silicon minerals. These minerals include opal, chalcedony, quartz, hematite, and pyrite. So you can see those mineral spectra, and we'll post this PowerPoint on YouTube so you can pause it and look at the different spectra of these different minerals. The next type of alteration is the argillic alteration. This plot shows illite, smectite, montmorillonite, calcium, and dolomite, and then kaolinite pyrite. This type of alteration occurs as wall rock alteration around veins and replacement zones and permeable lithologies. Now, this plot will actually show the spectral shift in aluminum content and temperature change away from the vein in a progression from illite at the top to the illite smectite and into the smectite. This is why using a field spectrometer is so important for mineral vectoring and understanding where these low and high sulfidation deposits are. Carbonates are also important in these systems and may reflect the condensation of CO2 from those deeper boiling zones. In these systems, there's also quartz pseudomorphs with the calcite, barite, fluorite, and calcium, magnesium, manganese, and iron carbonate minerals such as rhodochrosite. Now, steam-heated argillic zones alteration. Steam-heated argillic alteration develops above the water table and typically forms from very extensive alteration zones. It is associated with the condensation and oxidation of rising volcanic gases and is commonly observed in geothermal environments, including areas with mud pots, fumaroles, and native sulfur. In the field, these weathered outcrops are often characterized by resistant quartz alunite ledges formed where more friable material has been removed. These ledges are flanked by extensive bleached clay alteration zones dominated by supergene alunite, jarosite, and other sulfate minerals. In the plot shown here, sulfur pyrite, chalcedony, and opal are present, with the bleached clay zone defined by kaolinite and supergene alunite and jarosite. It is important to distinguish steam-heated argillic alteration from typical argillic alteration. Steam-heated systems are dominated by a kaolinite-alunite assemblage, whereas argillic alteration more commonly includes kaolinite, illite, and montmorillonite. Kaolinite varieties within these systems can exhibit distinct spectral shifts related to temperature differences, making field spectroscopy a critical tool for this mineral identification. And then finally, propylitic alteration. This alteration typically develops in the outermost zones surrounding mineralized deposits, and they can extend regionally beyond the main ore system. The plot illustrates characteristic mineral assemblages, including the magnesium chlorite, iron chlorite, epidote, illite, smectite, zeolites, montmorillonite, and calcite. Distinguishing between magnesium chlorite and iron chlorite is important for interpreting alteration intensity and fluid evolution. These minerals can be effectively differentiated using a field spectrometer, again, as variations in chemical composition produce differences in their spectral wavelength absorption features. Now to discuss high sulfidation systems. So high sulfidation gold copper systems form through the interaction of high temperature acidic magmatic fluids with host rock, producing strongly zoned hydrothermal alterations followed by a sulfide deposition containing gold, copper, and silver. Ore formation is strongly controlled by its permeability, which is influenced by lithology, structural features, brecciation, and changes in wall rock alteration and mineralogy with depth. A key exploration challenge is distinguishing these mineralized zones from generally non-economic acidic alteration styles, including lithocaps, steam-heated alterations, magmatic sulfur zones, and acid sulfate alteration. Classic definitions describe epithermal high sulfidation systems as forming at temperatures below 300 C and at relatively shallow crustal depth. So here you can see a diagram of a high sulfidation area. So epithermal deposits in an exploration context. In field exploration, the term epithermal refers to gold, silver, and copper deposits formed from a magmatic arc environments at relatively shallow crustal levels. These deposits typically form above porphyry copper gold systems, commonly at depth less than 1 kilometer, and are often associated with subvolcanic intrusions. Higher level epithermal mineralizations generally develop later in the paragenetic sequence and may become telescoped onto earlier formed deeper deposits. In some cases, epithermal systems overprint or coexist with porphyry systems that are either older or part of the same magmatic hydrothermal event. In strongly dilational structural settings, porphyry-related mineralization may extend upward and outward into the deeper portions of the epithermal environment. In summary, high sulfidation deposits develop in settings where volatile, rich magmatic fluids rise to higher crustal levels. Volatiles evolved from depressurized fluids to form a two-stage hot acid fluid. Initial stage reacts with the host rock to produce characterized zoned acidic alteration. Later, liquid-dominated fluid phase deposits sulfides, characterized by pyrite with anargite or other low-temperature polymorph leucine. So, magmatic rocks interpreted to represent ultimate source of ore fluids, common associations of high sulfidation deposits. They display associations with porphyry copper systems of similar ages. Fluids responsible for formation of high sulfidation deposits rarely evolve into gold-rich lower sulfidation style ores. And so here Here's a model for a high sulfidation gold system showing the different alteration zones and the feeder structure. So to point out some of these alterations that we'll see, the advanced argillic alteration is going to be in this upper region of the system. Now in the core of that zone of the advanced argillic alteration, you can find the vudgy silica type alteration. So you've got different types of alterations that can occur in one area. There's a type of argillic alteration that can occur, and this is called argillic to intermediate argillic, and this alteration is found between the propylitic alteration and the advanced zones here, and the propylitic alteration being that outermost alteration zone. So all these alteration zones here have different mineral assemblages that we'll talk about. So high sulfidation alteration types is acid alteration, advanced argillic, argillic intermediate, and propylitic. So here we're looking at the major alteration styles. Starting with acid alteration, this is typically the most intense style, includes vudgy silica and silicic zones. These form through aggressive acid leaching, where most primary minerals are removed, leaving behind a residual silica framework. Moving into advanced argillic alteration, we see a strong mineralogical zoning, controlled largely by temperature. Higher temperature conditions are characterized by minerals such as pyrophyllite, diaspore, and dicite, while cooler conditions transition into assemblages dominated by alunite and kaolinite. Outward from the core, we transition into argillic to intermediate argillic alteration. Here we see progressive mineralogical changes from illite into mixed layer illite, smectite, and eventually montmorillonite. In many cases, these zones develop gradational envelopes, including chlorite-bearing halos surrounding illite-rich veins. Finally, in the outermost zones, we have the propylitic alteration, which is typically characterized by chlorite-bearing assemblages. These represent lower temperature, more distal alterations, and are useful indicators for vectoring towards hydrothermal centers. Understanding these mineral transitions is critical in using a high resolution field spectrometer is critical to identifying these minerals in the field. So to take a closer look at vudgy silica and silicic alterations, which represent some of the most diagnostic features of high sulfidation systems. Starting with the plot on the left, this shows vudgy silica alteration characterized by assemblages including alunite, jarosite, quartz, sulfur, pyrite, and hematite in that order. This alteration typically forms along structural zones or as replacement bodies within permeable lithologies, most commonly within the core of advanced argillic alteration zones. Vudgy silica represents an extreme form of acid leaching where aggressive acidic fluids remove most primary minerals and leave behind a porous residual silica framework. This alteration is commonly developed in the upper levels of epithermal systems and may also occur in the upper portions of telescoped porphyry systems. Looking at the plot on the right, we see silicic alteration characterized by quartz, chalcedony, alunite, barite, hematite, and pyrite. Silicification involves the addition of silica, which fills the vugs created during intense acid leaching and strengthens the rock. Silicification is very common in high sulfidation environments and can sometimes be confused with intense quartz stockwork developed near the tops of some porphyry systems. So careful in your interpretation. Up next is the advanced argillic alteration. This plot shows pyrophyllite, topaz, zonite, dicite, alunite, and pyrite. So this alteration type is going to be found in the upper region of high sulfidation systems. It can occur in the lithocap of the porphyry system as well. The progression, neutralization, and cooling of high sulfidation fluids by rock reaction actually produces an alteration moving away from the core, in which zonation is characterized progressively outwards by mineral assemblages dominated by the alunite, pyrophyllite, and even the kaolinite chlorite clays. Next, we'll look at the intermediate argillic alteration. This plot shows mineral assemblages including kaolinite, illite, mixed layer illite, smectite, montmorillonite, quartz, and pyrite. One important point is that argillic to intermediate argillic alteration can develop independently from advanced argillic alteration. These zones commonly occur between the outer propylitic alteration and the inner advanced argillic core. Mineralogically, this alteration often shows a progressive outward transition, moving from illite-rich assemblages towards mixed-layer illite, smectite, and eventually smectite or montmorillonite-dominated zones as temperature decreases. In some cases, gradational envelopes are present where illite-dominated veins transition outward into mixed-layer clays and may be associated with chlorite-bearing halos surrounding the illite core. And then here we have our argillic alteration, and we have the minerals associated, including kaolinite at the top, illite, smectite, montmorillonite, quartz, and pyrite. And last but not least, we have our propylitic alteration. And propylitic alterations can be regional in scale, but is most commonly developed in the outermost zones of hydrothermal systems, represents a relatively lower temperature alteration compared to the more central alteration types. Key diagnostic feature is the presence of chlorite, and distinguishable between magnesium-rich and iron-rich chlorite is important. These chlorites display different spectral wavelength positions compared to minerals found in intermediate argillic assemblages, which is why using a field spectrometer is so important. In the plot here, we have magnesium chlorite, iron chlorite, epidote, calcite, and pyrite. Now, how do you use a spectral evolution spectrometer to identify these kinds of minerals, and what does it look like when you're using it in the field? So stepping back to our EasyID software, we have the match analysis. So this is how you would port in a built-in library, but you can also right above in the drop-down is load an EasyID library file where you can actually load in spectra of known mineral samples and create your own custom libraries to match to in real time. Now, when you are matching the spectra to your library, it'll look like this. So you can manipulate these match regions. Those green regions are match regions, so you can target specific absorption features and decompose spectrally complex samples. So if you're using a 10 millimeter spot size, maybe you have a mixture of different minerals that you're sampling. With one scan, you can actually target specific absorption features using those match regions. And you can slide them around, make them wider or smaller, and you can use those match regions as a batch analysis as well. So for batch analysis, we also have these mineral scalars that will help you identify where absorption features are taking place. And in the batch analysis, this will be exported as well as part of your data analysis. But the batch analysis will allow you to take all of your samples that you've collected in the field or along core samples and apply different match regions that you've customized and give you the best results. So you can use different statistical analysis and process them all at once, as well as using different combinations of match regions within that. And I would recommend our mineral identification webinar, part 1 and part 2, for this in more detail. But you can create Excel documents giving your top 3 to 5. It's totally customizable, your highest scoring R-squared compared to the mineral libraries that you're applying your scans to, and it will export as a CSV. So very easy to use, very easy to read your identifications. And then you can also create score tables here as well to actively look at what the best match is in real time. So as you're scanning along, you can tell exactly what and log what you were matching, what mineral it was matching to. So you can use that to identify and vector where your dig site should be and where the economically viable minerals may be. So thank you very much for listening today. Please reach out to me with any questions. I'll open it up to questions now, but thank you very much. I know it was dense, so have a great rest of your day. Thank you.